not an action potential. It's a small response. It's an excitatory postsynaptic potential. So we know now that the change is that the motor neuron is responding less. That was a huge finding, because that means that actually there's learning in this very simple circuit, and the learning is happening in this one synapse between the sensory neuron and the motor neuron. And while normally there's many sensory neurons and many motor neurons because you have many muscle fibers, you can reproduce this learning by just using 2 cells. So that's crazy. You can actually look at learning taking place by looking at just 2 neurons. But it still doesn't tell us all the story. So after repeated stimulation of the presynaptic cell, the postsynaptic response got smaller. But it could be because the presynaptic cell is releasing less neurotransmitters, or because the postsynaptic cell actually has a lower number of receptors. So either the presynaptic cell is sending the same message, and the postsynaptic cell is responding less, or the presynaptic cell is sending a weaker message, and therefore that's why you get a smaller response. Does that make sense? The 2 possibilities? There are ways to figure them out, but you guys need 110B before to figure it out. So you're just going to have to believe me that what actually happens is that there's a reduction in presynaptic release. The actual mechanism of habituation is that the sensory neuron releases less neurotransmitters every time it's stimulated. If we go back to this for a moment, where we saw that this goes down and then it comes back up, and it goes down and it comes back up, and it goes down and it comes back up. Habituation only lasts for a small amount of time. So if you wait 30 minutes and you stimulate the sensory neuron, you actually get the same original response. So you could almost think that if you're stimulating that neuron over and over and it's releasing neurotransmitters over and over, maybe it just doesn't have enough time to replenish the pool of neurotransmitters. But if you give it enough time, it will start to have enough neurotransmitters back in the terminal. Maybe, maybe not. Yes? So it's a reduction in presynaptic release. So if you were to go back to here, it would be less transmitter being released from the presynaptic terminal. Yes? Yeah. It means you have to release some level of neurotransmitters, but it doesn't mean you have to release everything that's there. So you're going to see that there are mechanisms by which cells can regulate what percentage of their pool of neurotransmitters they have to release. One action potential doesn't release all of the neurotransmitters in a neuron. It releases actually a small amount.
So the same stimulus will cause the same number of action potentials?
Yes. Yes, and you're going to get a different number of vesicles being fused into the membrane and releasing neurotransmitters. Yes.
And will you forget it if it's time dependent?
If it's time dependent, so the belief is that there is, so the explanation people have come up with is there's a finite number of vesicles in the terminal. So imagine there's 100 vesicles. You stimulate once, you release 40. Then you only have 60 left. You stimulate again, calcium comes in. Now the probability that calcium will find the vesicles is a little bit lower because you only have 60. So instead of releasing 40, you may release 30. But now you only have 30 left. So then calcium comes in, and the probability is going to be even lower, and also you only have 30, so you're probably going to reach even less. And what happens in neurons is that over time, you're going to make more neurotransmitters and put it in vesicles, but that takes time. So if you wait at like 10, 15 minutes, now you get enough time for the cell to make more vesicles, make more neurotransmitters, so now you have 100 again. Habituation at this level is temporary. You can make it permanent, but at this level it's temporary. Does that make sense as a kind of mechanism? Yeah.
So this circuit kind of forgets over time.
Yeah, so habituation is considered a form of short-term learning. It will last like several minutes, but...
That's actually my question. I was going to say, if you have misnomer, all this short-term memory maybe not.
It depends. So neurobiology of long-term memory is something that lasts longer than 30 minutes. It's completely arbitrary. It pretty much links to the idea. In neurobiology, psychology has a different definition. In neurobiology, it's because it's really hard to continue to record from neurons for more than 30 minutes. So if a neuron made it to 30 minutes in your recording, the assumption was that it would have probably made it to longer. But your neuron died because it just made a hole in it when you were recording. So people who work on extracellular recordings have a 2-hour limit. They think that long-term learning requires changes that last at least 2 hours. But that's because they're looking from outside of the cell, so the cell is still alive. That's easier to do. Psychology has a much bigger range. They have priming, they have short-term memory, they have medium-term memory, they have long-term memory. So they have many more stages. When you're doing experiments, it's a little bit harder to make that. But yes, so yes, a little bit arbitrary. We consider short-term learning several minutes. Are we okay with this and the mechanism? Questions about it? We're going to switch to sensitization. Yes? Is that a question or was that okay? Okay. Yeah.
How did we determine that it wasn't a constant shape but rather to cause the drop in response?
How could it be a time issue but not a chemical issue?
Because supposedly you mentioned how we might have 100 and then going down to 60.
Yeah.
How do you know that that's not like a physical limitation versus the cell saying, all right, we're getting so many stimuli, we're not going to respond because it's not natural.
What would be the mechanism for the cell to make that judgment?
Well,
That's the what we're looking for. What is the mechanism by which the cell knows that it's getting repeated, stimulated several times and changes what it's doing?
But sometimes if you, there's a refractory period, and how do you know that this is a part of a refractory period?
The refractory period actually potential is about 2 milliseconds.
Well, I mean, how do you know that it's not something like that, that you're just stimulating it so quickly that it's just going to respond shorter?
But that is a mechanism.
So,
So what underlies that refractory period where you respond less?
well, I'm assuming there's something to do with the serotonin that we're talking about, but how do we know that it's not, how do we know that there's something that's causing the cell to stop reacting this bigger?
So the idea like you run into less vesicles, that is a form of a refractory period if you want to think about it.
Yeah.
You're less able to produce the same output. So how do we know it's this and not something else? Nobody has found anything else that matches in its time course and correlation with the actual behavior that you see in the animal. But that's kind of the question. When you start with this, you don't know what it is. You just kind of start looking at what are all the possibilities, and then you find one thing that its time course and behavior matches it what you're seeing in the animal, and that is highly likely what it's underlying it. There may be other things that have the same time course, but you don't see it. Does that make sense? You always need to have in the end a mechanism. Time by itself doesn't do anything. If time is an effect because something is happening during that time, and you need to figure out what that thing that's happening is. Does that make sense? So, the synapse between, by the way, this synapse here is a glutamatergic synapse. It releases glutamate. Sensory neuron to motor neuron releases glutamate. Motor neuron to muscle releases what? Acetylcholine. So now we're going to look at sensitization. Sensitization is an experience we've all had. If something, well, maybe we've all had it. But imagine that someone's poking at you and is really, really innocent, and suddenly somebody slaps you. The next time that you get poked, you're actually probably going to respond much more because you've kind of been taken to a different state. Or if you're walking in the middle of the night and you hear a sound that could be like a shot or it could be like someone screaming, suddenly you're going to become much more attentive to what you're responding. But it's not specific. Like, it's not that you're associating the slapping with the thing that happened in your arm. You don't. You just got slapped and you're just going to be attentive to everything. So it's a form, it involves two stimuli, but it's not an associative learning. If I were to give you an electric shock, you'll respond more strongly if I poke you, if I talk to you, if I slap you, if I pull your hair. You'll just be more responsive. Does that make sense? So it's not specific. So you can take shock. So, the animal has habituated, and then you test him, and he's still kind of habituated to the response. The way that they habituated the animal is a little bit different. It's called long-term habituation. We will not talk about how that works, but you can actually teach an Aplysia to habituate for long periods of time. So then, if I have an habituated Aplysia and I give it a tail shock, right before I do the tactile stimulus, I get a bigger response. And if I do 4 single shots, I get a even bigger response. This is 1 shot, 4 shots. If I do 4 trains of shocks for 4 days, then I get a huge response. I don't exactly know how, 1,000 times longer we roll than we get normally. And over time, this will go back to normal, but the more you shock the animal, the longer it will take to go back to normal. So the idea with sensitization is that you can actually increase a response to a stimulus by giving it an external, completely unrelated yet harmful stimuli, or at least scary. And this is kind of the sensitization circuit now inside of an Aplysia. So here's the tail, here's the head, here's the siphon, here's the gill. So we're in the same place as before. When you touch the siphon, here's our sensory neuron. That stimulates the motor neuron that makes the gill contract. Are we okay with that? This is the same linear pathway. And now we're going to incorporate the information that's coming from the tail. So when you give a shock to the tail that activates a sensory neuron, that will release serotonin right here. So we're going to look at this specific area. The release of serotonin is not onto the postsynaptic side, it's to the presynaptic cell. So we'll talk a little bit about that. We're going to take this and we're going to simplify it in our drawing so it's easier to look at. So now we have the siphon, sensory neuron, motor neuron muscle, our familiar circuit. And I'm adding here a stimulus in the head of the tail, going to one specific neuron that is synapsing on the sensory neuron. So it's going to the axon terminal of the sensory neuron. And now I can do this pathway till it habituates. So I stimulate several times, and now it's habituated. So I stimulate the sensory neuron, and I get a very small response in the motor neuron. Are we okay to where we are? And then I stimulate this pathway once, and now I get a bigger response to the motor neuron. So I stimulate this pathway, and now when I test the reflex, I get a bigger response to the motor neuron. There's different ways of looking at this. This is the postsynaptic response that you measure in the motor neuron. So before you sensitize, you get a certain response. When you sensitize, you get a much bigger response. And this is how long the animal is withdrawing its gills in terror. The animal, if you do a control where you just test twice, you don't get a difference. This is then the animal that was sensitized. You test the withdrawal reflex that is now habituated, you get a very small response. You give a shock, you get a huge response. And you can prove that it is this synapse because you could block the receptors for serotonin and show that there's no sensitization. Or you could just dump serotonin and you would get sensitization. Remember we talked about how can you actually prove that something is involved in a pathway? Like, is serotonin necessary? Well, we block the receptors and we don't get sensitization, so yes, it is necessary. Is it sufficient? You drop serotonin without even touching the rest of the animal, you get sensitization, then yes, it is sufficient. Yes?
So axon terminals have receptors?
Oh yeah. Everything in a neuron has receptors. Cell body, dendrites, axon terminals. There's dendrites between there's synapses between dendrites, they're called dendritic synapses. There's synapses between axons, they're called axonal synapses.
What's the difference?
We've been lying to you all the time. You'll see this in were to be any questions in the exam, please go with the linear way in which it works. There's exceptions to everything. But if you were to say, where do we normally see action potentials in the axon? Where do we reach neurotransmitters? The dendrites, the axon to the dendrites. That's kind of like the straightforward thing. This is the synapse that we're looking at, though. This is an axoaxonic synapse. And this is our last slide, I think. Yeah, pretty much. So, the idea is the following. Normally, the sensory neuron releases neurotransmitters when the action potential arrives. And here we have this, the L29 neuron releasing serotonin, which binds to a metabotropic receptor involving G protein pathways, activates amylyl cyclase, and activates PKA. So the mechanism of sensitization, which changes the behavior of Aplysia, is based on a cyclic GMP pathway. We keep coming back. You guys may have wondered why you have to learn the cyclic GMP pathway. It's everywhere. You'll find it in everything you ever look at. And how is it that activating a PKA makes you more or less sensitive? So it turns out that the effect of serotonin is it makes the sensory neuron release more neurotransmitters. The final effect of serotonin is that you release more neurotransmitters. I will not ask you this because we've already started talking about action potentials, but the effect of serotonin is it makes the action potentials wider. So this is without serotonin, with serotonin. And as a result of that, more calcium comes in, and we can actually release more neurotransmitters. So again, the effect of serotonin is to increase the amount of neurotransmitters that the sensory neuron is releasing onto the motor neuron. Yes?
So is this mostly for like learning stuff with reflexes and the process of me actually learning school material is actually different?
So that's a good question. Learning school material is a form, it also involves changes in synapses. So whenever you look at an animal and you train an animal to run a maze, which is it involves some form of spatial memory, but also what's called sequential memory. So it's very similar to learning how to walk from point A to point B, which is learning a track. If you block certain kinases, like CAM kinase 2, the animal doesn't learn it. If you block certain receptors, like glutamate and MDA receptors, the animal doesn't learn it. And if you look at what's going on within the hippocampus, the structure that's learning this, there's actually been modifications to the connections of the synapses that are already there. So we really believe that this underlies all the ways that we learn. It's just about which circuit you're looking at and the precise way in which you change that synapse. But it does look like most of the time we're just changing synapses that are already there. Yes? Arginine? No. LTD? Yeah.
We increase the sensitization here, and then over time, like, or in an earlier step, it decreases. Does this cause it to decrease faster? Then, like, if you keep stimulating it, it drops at a consistent rate.
Yeah. So if you do many more shocks, it takes longer for sensitization to go away. And the reason for that is that you actually start making changes in gene expression at that point. All long-term